know the integration form? Yeah, there you go. That's the one. This is the same thing. So delta U over cycle, which is this one. So what's my delta U over cycle? Favorite number of in thermodynamics? You start from one state, you do whatever you want and going back to same place. So there is no change. So this is the most important sort of insight. And then from here we can get something very useful. So over this cycle, heat goes in and out and work. So I'm just going to put everything that is happening here. So over the cyclic process of Carnot cycle, QH, QC, and W, they are going to be zero. So this is the one that's going to be obvious from the considering that internal energy is a cycle. How about that? Very good. And finally, he did this one. This is sort of the hot source, cold surrounding, and this is doing the work. And this mu, okay, well, eta, this is called the Carnot efficiency. Carnot engine efficiency, if you want to call it. So I want to know Carnot engine efficiency. Well, that's. I will just say Carnot efficiency. Okay. Since actually this is the whole reason that he wants to know. Okay, given that we can do the cyclic motion as an engine does, and I define everything is reversible. This must be the maximum work at the expense of heat. You're using it and you're dumping to the surrounding, and that's the one. So, and he defined the efficiency, eta. What's my efficiency? You see my poor man's writing here? It's always this, right? I want to know how much I put using it and how much I'm getting out of it. How much you're putting into it as an engineer? How much you're putting as an engineer? You're putting? What are you putting into the this is your system, right? How much you putting in? How much dollar do you pay to buy this hamburger or something? QH. There you go. And what do you care? What do you want to know?
For work.
Right. Yeah, I don't care about this, right? I care about work. How about that? Are you happy with this? Not happy. Yeah.
I have a question. So, in the adiabatic compression from D to A,
Yeah.
why isn't there work going into the system?
Work going into the system. Because of the Q is 0. So, but there's a delta T is going up. So therefore, this one is this way. So your work is a positive. Okay? Temperature from cold temperature to the high temperature. Okay? So delta U is Q plus W. Once again, that's a 0. Okay? And because of this one is essentially the same as CV dt, and temperature going up, your work is going up.
Oh, so the one work term represents the work from both the adiabatic experiment.
Which one?
The work term that you had there.
The term here, this is a work over cycle. Yeah, that's a good
So that
question.
counts. So that counts for the work from both adiabatic.
Yeah, that counts from here, 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 here. If you do the graphical subtraction, that's a negative area, positive area, positive area. This is what is left of as a negative area. Okay, but I'll put a magnitude as an area of the mode. So that's a good thing. Thanks for clearing that. this is a work over the cycle, and that's a, what it's called, in a way, people also say there's a network, right? It's not network, but work over a net, okay? The overall work that you produce. Okay? But I'm not happy with this. You know why? If I do this, Carnot efficiency must have a, I have a Carnot efficiency of 0.5, minus 50%. Am I right? Do you remember this? Where did I go? By definition, this is my surrounding and work is negative here, right? And your QH is positive. So this is actually negative. So you cannot do that. So people are lazy, so they just, this is a more conventional way. I don't care about the sign, let me just say the magnitude, right? But because we know exactly what it is, so now this is a QH minus W, right? I know work is negative, and that's really the birth of this, okay? Work is negative, yeah. And then what do you have? QH, going back to the equation that I like, that's one, right? So work over cycle, the internal change over cycle is combination of Q goes in and out and work. So this is a work, so I go to the other side, minus negative work, this is this, right? That's right, yeah. This is a QH plus QC. So don't be disguised. This is a positive, but this is a negative. Okay? So this is always smaller term than what it is, and this is a bigger one. And then I got I guess I got my final equation. As far as efficiency is concerned, is 1 plus QH QC. Yeah, I got this. So this is my Carnot efficiency, knowing that how much work can I get out if I dumping the work, dumping the heat to the surrounding, QC, while I'm kind of, this is actually, this equation is using for the jet fuel engine. I seen the GE scientist giving a seminar, and then he said, if you want to have a jet plane, the jet engine, all you do is burning the fuel to get the temperature up as high as possible, and your exhaust has a lower temperature, and those temperature gap is the one that creating the moving turbine. And there are other more complicated equations, but this is the one. Okay, but look at it. I'm not so happy with this. Why am I'm not happy? It looks like I can get it in using this nice equation, and I can get it in, but this is a quantity that I'm not used to it. Do you measure QC and QH? It's something that you want to do? What's the easy one to measure here? QH or pH? This one I can measure that, right? Right? Will it be nice if I can change that equation into a temperature relationship? That would be amazing, right? And that's what's happening here. Because, so what I do now is I'm going to steal this, although historically this happened this way. It's not happened this way, but because we know we have a defined relationship for DS is this, I'm going to have an additional help. Okay? So see what I'm doing now. Okay? I guess this one can see it here. So DS is Q reversible over temperature. Okay, I get that. Oh, this is a state function you told me before. So can I, if I do this, that must be guaranteed to be 0. No doubt it, right? Okay, and let's do that. My first component here, you see the isothermal? What's my temperature, isothermal reversible? The first one, expansion, A to B. This one, I need to slow down and you need to write it. Okay? My first one is A to B expansion, isothermal. So what's my temperature for delta S? Well, you know what, if you want to call it cyclic is, this means ds 1 to 2, or A to B, B to C, C to D, going back to A. Okay? So I'm just talking about A to B. Right?
T.
Yeah, so what's T? What's my Q reversible?
0.
Isothermal. First one is isothermal.
No, negative work.
First one is isothermal, right? You can say adiabatic.
Inner T.
Energy.
Inner T times.
Is it QH? I call it QH, right? I call this one, let's go here. This is an isothermal. I call QH is heat is going into the system to maintain the temperature to be constant. And this one is a reversible, right? I didn't write reversible, but this is a reversible heat on the isothermal condition at high temperature. So therefore, my first equation of entropy from A to B is this. Right? Make sense? Good? What's my second one? Adiabatic. Reversible Q is?
0.
So therefore, B to C?
0.
There we go. My favorite number. What's my third one? Now, temperature is same as
QC over
EC.
TC.
And what's my Q reversible?
QC.
We call it QC. What's my last one? Once again, 0. Right? So I'm all of a sudden that I got this equation that seemingly looks like they are showing the relationship between heat and the temperature, right? Right there. So what you have is, because entropy change over cycle is 0, this is a QH, pH, QC, EC. And then I'm interested in QC over QH, so let's say QC over QH. And then there will be minus TC. Yes, the equation. So using this equation, okay, so I'm going to put this one down and I'm going to swap it. Let me do that actually. So QH pH is minus QC TC, and then I'm going to put this one, we keep this and this one up. Yeah, this equation is true. So therefore, this equation, all of a sudden, there's something that is much more easier for me to define, which is minus pH TC. So that's the equation for Carnot cycle efficiency. Okay, let's take a little pause here.